Back in 1993, there was an episode of Star Trek Next Generation that featured four of arguably the smartest, highest IQ individuals in the last 500 years or so. And they were on the holodeck, which involves three-dimensional projections of people. And they were playing poker. One of the people playing poker was Data, who was an android in the series. Then there was a holographic projection, which was an actor playing Isaac Newton. There was another actor who was playing Albert Einstein. And then the fourth player was Stephen Hawking himself. You might recall Stephen Hawking was a brilliant physicist, cosmologist out of Cambridge. He was born in 1942, and at the age of 21, he came down or was diagnosed with a slowly developing form of ALS, or Lou Gehrig's disease, a motor neuron malady, which eventually took his life in 2018. So he died about 7 years ago. So the four of them are playing poker and having this marvelous conversation. In any case, I mention that because Isaac Newton was considered to be one of those brilliant scientists that was part of this group of men playing poker. We're going to talk an awful lot about Isaac Newton and some of his ideas and discoveries. First of all, I'd like to say that Isaac Newton, and we'll circle his name right there, was a Christian, a devout Christian. In fact, when we look at the complete body of work that he produced during his lifetime, he was born in 1643 and died in 1727. So he lived a good long age for people of that time. Most of the work that he did, most of his writing was actually in the area of theology. You could say that maybe the physics for which he is best known represents maybe 5 to 10% of everything that he worked on. As a devout Christian, and you can read his giving glory to God in the opening pages of one of the most famous scientific works of all time, the Principia Mathematica. And in that introduction called the Scholium, he talks about giving praise to God, in fact, that it takes somebody like God with his attributes and character to be able to create a universe that has the order and the consistency, the patterns and regularities that it does. Unfortunately, during history, more recently, within the last 50 years or so, there are those who have ignored Isaac Newton's Christian testimony and background and said that he paved the way for not needing there to be a God because the whole universe was mechanistic. And therefore, because of understanding the mechanisms, we no longer need to understand the person who is behind the mechanisms. Kind of like saying that once you understand the automobile, you don't need men like Henry Ford and other inventors. I should also mention, though, that Isaac Newton struggled with one particular doctrine, the doctrine of the Trinity. And, of course, all of us, to some extent, wrestle with this doctrine because it is just so profound. It is just beyond the capabilities of the finite fallen human mind to comprehend. And yet we know from Scripture that even though the Bible does not mention the word Trinity at all, the Bible reveals a God who is triune. God chose in the pages of his revelation, called the Holy Bible, to reveal himself as God the Father, God the Son, God the Holy Spirit. So with that as a little bit of background to Isaac Newton, let's move on through this introduction. And you'll notice in this opening paragraph, they say that there are limits to Isaac's laws of motion, which we'll be focusing on in this chapter, as well as this law of universal gravity. And one is that when you get really, really small, subatomic, Newton's laws of motion actually become a special case of a bigger picture, and that is quantum mechanics, which we'll study second semester in a later chapter. At the same time, when you begin to talk about speeds that approach the speed of light, relativistic speeds, we say, then again, classical mechanics breaks down, or better, we should say, becomes a subset of a bigger picture, Einstein's theories of special relativity at the beginning of the 20th century. So you can see that in the first half of the 20th century, both quantum mechanics and relativity broaden our idea of physics. And so when we talk about classical physics, it's between these two extremes. It's not that they're not true, it's that they're based upon certain assumptions of ordinary speeds, like we see when we throw a baseball or drop something or watch planets go around a star or stars move through space. And it also assumes that we're talking about larger particles bigger than an atom. Another point I want to make here is with these words, simple and sensible. Even though your textbook does not integrate in anything having to do with God's word or the character and attributes of God, everything here is based upon him and who God is. And so when we look at the three laws as being simple and sensible, please remember the word simple is not the same as the word simplistic. Simple means it's capable to be understood, by an elementary school or middle school or a high school student who's just beginning a study of physics. It's a stepping stone to more and more complicated and intricate and complex ideas. And it's also sensible. It meshes very well with our intuition and everyday experience. Sensible is another way of saying it is rational. And so we can ask the question, why is the universe rational? And I'm going to write that down here. Why is it rational? Well, the universe is rational, the Christian would say, because it's created by a rational God, a God who is all-knowing and perfectly logical and perfectly rational and infinitely logical and infinitely rational, way beyond you and I are capable of being in our finite and fallen state. So the universe is rational because it's a reflection of a rational creator. Now, other people with other worldviews will try to come up with some other explanation. But those explanations, many would think, and I certainly do, are not the best inferences, do not lead most logically and easily to the idea of a rational universe, the idea that God is rational. And by the way, you can study John 1:1. In the beginning was the Word, and this is capitalized because it's referring to the person Jesus. But in the Greek, it's the word logos. And logos in the Greek refers to logic or rationality or reasonableness, as a way of describing Jesus himself, Jesus Christ himself. So not only, though, does the universe have to be rational, but you and I must be rational as well. If we are not rational, we would be unable to study a rational universe. If the universe were not rational and we would not be able to understand a rational universe. So your textbook correctly identifies that these laws of motion, like so much else in physics, are simple but not simplistic, and sensible or rational. This is a good description of the universe God created. Why did he make it simple? He gave us all kinds of entry-level ideas and understandings that then can become the foundation of deeper and more profound understandings. And then those understandings, once we establish the second step or the second rung in the ladder, lead us to the third and the fourth and the fifth and so forth. And we're going to be going on and on and on through all eternity. When Jesus comes back, even in heaven, because heaven and earth become one, of following these deeper and deeper levels of understanding and amazement of God's rational universe. Now, another thing we need to point out, as long as we're talking about philosophy, is when we get to Newton's universal law of gravity, we're going to ask the question, why is this called universal? After all, human beings at most have only traveled in orbit around to the far side of the moon. That's as far as we've ever gone in terms of leaving the surface of the earth. And certainly we've sent satellites and probes that have even exited our immediate solar system, but that's very, very small compared to the universe. Is it rather audacious or presumptuous or arrogant on our part to say that this is a universal law? And we're going to comment more on that when we get to Newton's universal law of gravity. And next, something about theories. A good theory should not only explain what you observe, it should also be a very straightforward or inference to the best explanation kind of theory. We don't want to make it unnecessarily complicated and convoluted. That has to do with something called Occam's razor. But a good theory should also be predictive. It should lay the foundation and suggest something that we ought to find if we can figure out an experiment to test that theory. And so this theory suggested the idea of dark stars. What if you have greater and greater and greater amounts of gravity, and it begins to pull matter closer and closer and closer together until eventually we have this idea that maybe there's something called a black hole, which of course now is a ordinary part of our understanding of the universe. All right, let's move on to the idea of forces. Now, I should mention from the get-go that we do not know what a force is, but we can describe it incredibly well mathematically, and we can categorize the different kinds of forces. We're going to talk about forces being contact forces, and in a later page, we're going to talk about field forces. And then we could say, here's some examples of contact forces, and here's some examples of field forces, because they all seem to have characteristics that are similar in terms of being a push or a pull. If the push or a pull is because of physical contact, like a tennis ball hitting a racket, or a hand acting on a racket, or feet down here pushing against the earth, or the earth pushing against the tennis player, these are contact forces. We can also talk about field forces where there is no contact. We'll get to them in a minute. Now, these contact forces all seem to involve something you should recall from chemistry: electromagnetic forces, forces that involve forces between particles, protons and neutrons, and atoms and molecules. And it's these forces that provide the solidity, the solidness that we often experience. And when these forces are really strong, like the forces that hold the particles that make the surface of the earth together and the surface of your feet together, that's why your feet can't go through the earth, or that's why your iPad can't go through the desktop if it's on a desktop, because those forces are too great to let the one be able to penetrate the other. Of course, if we're talking about the forces that hold particles together in a gas or a liquid, you can go through those things. You can dive into water and you can walk through the air. So obviously those electromagnetic forces are much weaker than the forces that make up solids. And so you might remember ionic bonding and covalent bonding and intermolecular forces, called van der Waals forces and hydrogen bonding and induced dipole forces. Those are the kinds of things we're talking about here. These are electromagnetic forces. Now, as far as prefixes are concerned in measuring the distance over which these forces act, we know from experience that gravity seems to act through thousands and thousands of miles. But forces between the protons and neutrons in a nucleus only seem to act through a very, very small distance. Sometimes we measure them in femtometers, which is 10 to the minus 15th, or nanometers, or micrometers. Micrometers 10 to the minus 6th. Nanometers would be billions, 10 to the minus 9th. Picometers would be 10 to the minus 12th, and femtometers 10 to the minus 15th. Notice that we do this by every third power of 10. Textbooks in physics used to use the angstrom a lot, which was 10 to the minus 10th. We don't use the angstrom that much anymore, but occasionally you see a throwback to that particular unit. The angstrom was sometimes designated as the letter A with a little circle over the top. But these would be units we would use when we're talking about the distance between particles in a nucleus. So we've got these protons and neutrons and intermolecular forces and intramolecular forces. So contact forces, here's some examples which require physical contact, and field forces. When we talk about field forces, we usually talk about the gravitational force, the electrical force, which is charge, or the magnetic force, which is iron. And you know that things can be under the influence of gravity, for example, of the Earth without touching the Earth, such as the moon or a satellite or an airplane. Charged particles without touching each other can repel and attract each other. And if you've ever held two magnets together, you can feel forces of repulsion when you have north pole of the magnet trying to come close to a north pole of the magnet, or south to south. You can feel that force of repulsion without them physically touching each other. Those are field forces, which was a radically novel idea in the middle of the 19th century. We'll mention it a little bit later. And there's a little analogy here in the text. I'm going to back up a little bit, beginning down here. If a proton in a hydrogen atom were the size of a ping pong ball, the electron would be the size of a bacterium and would be about 1 kilometer away, more than half a mile away. So an atom is mostly made up of empty space. Another way of looking at this is, let's say you had a hydrogen atom and you put it at second base at Busch Stadium. The nearest electron would be way out in the bleachers, the last bleacher seat, way out in the back of center field maybe, and would be, a little more than a dot. So an atom is mostly empty space. Now in this next paragraph, it talks about these intermolecular and intramolecular forces, these electromagnetic interactions between the charged particles, but it uses this term, the normal force, which we're going to get to later in the chapter. When we talk about a normal force, and your book will represent it with a lowercase n, I represent it with an F sub n as a normal force. And the normal force always means perpendicular to the surface. So if this is the surface of the Earth, and I have an object, let's say it's a box acting on it, the normal force is the force of the Earth pushing up on the box. And then the downward force is the force of the box acting on the surface of the Earth, which is called the force of gravity. Sometimes it's called the force of weight. Your textbook would use a lowercase w. They like to use lowercase letters. I like to designate all forces with a capital F and then a subscript representing what kind of force we're talking about. So for example, with tension here, I would talk about the force of tension, whereas your textbook might use a capital T for the force of tension. And for friction right here, I would have F sub F, but your textbook would use a lowercase f. Actually, a textbook and the capital letter T can often mean period of time, so they might use a lowercase t, but T also stands for time. So you can see why it's confusing, which is why I like to use capital letter F and then T for tension. So the strange thing about field forces is that somehow they could affect something without physically touching it, action at a distance. And of course, early in history, this would be before the 19th century, maybe this would be chalked up to mysterious forces or actions by the gods, weird things like that. But of course, to somebody like Isaac Newton, who was a Christian and therefore ruled out, the Roman and the Greek and the kinds of gods that might be present in animism, the god of the mountain and the god of the river and the god of the moon. And Michael Faraday, who was also a very, very devout Christian person. They would rule out those particular explanations for why something could affect something else without touching it. And they invented the idea that some things that are real are invisible. And they call these the field forces. And I already mentioned the three field forces of gravity and the electrical force and the magnetic force. Gravity we're going to be talking about in this chapter and most of first semester, whereas the electrical and magnetic forces we'll be talking about after Spirit Week. Now, there are basically four forces as we understand them now, and we're trying to combine them into one unified field force, one unified force. We call this the grand unified theory, the gut theory, so to speak, or the theory of everything, where we try to put all of these forces together in one set of equations. That we would say that if you go all the way back to the moment of creation, when the universe came into existence, there was only one force, and then over time that one force became these four forces, the strongest of which is the strong nuclear force, and this is what holds the protons together in the nucleus, even when they're separated by neutrons. The next strongest is the electromagnetic force, which we've been talking about in chemistry a lot. Then the third weakest force is the weak nuclear force, which has to do with nuclear decay, alpha, beta, and gamma decay. And then by far and away, the weakest force of all is the gravitational force. It just seems strong to us because the particles we're talking about are a lot bigger than protons and neutrons. Those of you that are still awake at this point in the screencast will remember that planets and stars and moons and comets and asteroids are a whole lot bigger than protons and neutrons and electrons. And that's why the gravitational forces seem to be as big as they are. But if you break it down, and say the amount of force per common unit of mass, the gravitational force is many, many, many times weaker. Somewhere in the order of about 10 to the, I'm trying to remember if it's maybe 46 power. That's the difference between the strong nuclear power being that many times stronger than the gravitational power. That is a huge difference. All right. So the strong and the weak are in the very, very close proximity to the size of the nucleus. And then the gravitational and the electromagnetic actually extend out and go on and on and on, though eventually at some point they approach zero because they become impossible to measure them when they become so weak. So, for example, the gravitational attraction on our sun from some object on the other side of the galaxy would be impossible to measure It would be 0.00000 many, many times over. All right, the laws of motion. Newton is very famous for 3 laws of motion. He's also famous for co-discovering calculus and coming up with a systematic way of taking measurements and performing calculations, which is an absolutely necessary component for science and physics especially, to be able to make any progress and to form a foundation upon which you can build and build and build and build step after step after step. And of course, the only reason you can have a systematic method is if the universe itself operates systematically according to patterns and regularities. We see patterns and regularities all the time in our everyday observation. And we believe these patterns and regularities extend out into outer space. Now, these patterns and regularities can be described by laws. We can say, for example, there seems to be a pattern or regularity that when you increase the temperature of a gas, the volume gets greater of that gas. That's a pattern or regularity, and we can convert that into a mathematical law by introducing a constant, that the volume equals some constant times temperature. And then we can begin to take measurements and do calculations using our mathematics. But why are there patterns and regularities? Why is there this consistency and order in the universe? And again, it's because creation reflects the Creator. I think the inference to the best explanation is that the way to explain the patterns and regularities that we see everywhere in the universe, and why we have every confidence that when we get them right, they will be true tomorrow and next year and 1,000 years from now, and they will also be true anywhere in the universe, is because they reflect the character and personality of God. God is a covenant-making and a covenant-keeping God. And not only does he make covenants with people, and we can read about that theology, especially in the Gospels and the Epistles, but we see all the way back in Genesis that God makes covenant promises with his creation. We also see this in the book of Jeremiah. God makes covenant promises with his creation to be faithful to the order and the consistency. This does not mean that God is prohibited from acting outside of or within these patterns and regularities, something we might call miracles. But because God is a covenant-making and covenant-keeping God, we see that in his creation. Hence, the universe is systematic, and we can describe these patterns and regularities, these systems, and perform our calculations. All right, Newton's first law. Newton's first law goes all the way back to when, before the time of Isaac Newton, and again, this would be almost about half a century, when Galileo devised a thought experiment that if something is rolling down an incline, it's going to travel a certain distance, and if the incline is steeper, it's going to travel even farther, and if you begin to imagine there not being any friction, theoretically, it should be able to go on and on and on and on and on. So he's laying the foundation. Galileo was another devout Christian man who ran into trouble partly because of his sarcasm and partly because of some political issues that the Pope had to be dealing with. And various mythologies have developed around Galileo, like he was tortured, or he was Mr. Science, and he was anti-theology, and none of those theories, those ideas are true. And we can talk more about Galileo later. But in any case, this first law of motion has 3 parts to it. Begins right here. If an object is moving, it's going to continue to move at that same speed on and on and on and on, unless there is some other force acting on it, like friction, that's going to change it, or some other force that might change its direction or its motion. By the same token, if something from our frame of reference has no motion and appears to be stationary, it's going to stay stationary. It's going to stay what appears to be at rest from the perspective. Think about the idea of frame of reference in the previous screencasts. So if an object is in motion, it's going to keep on moving. If an object is at rest, it's going to stay at rest unless an outside force acts on it. So there are three parts to that. It's going to keep on moving at the same speed. If it appears not to be moving from some frame of reference, it's going to stay at rest unless you get a non-zero or outside or unbalanced force acting on it. Well, that unbalanced force is going to be what's going to cause it to accelerate, which becomes an important factor in the second law of motion. Now, we can talk about external forces and internal forces. External forces are going to act on an object from that object's environment. For example, gravity is acting on you. Gravity is not in you, so to speak. It's acting on you from the gravitational force of the Earth primarily, but also the moon and the sun and everything else around you. The internal forces are within the object, and this is where that chemistry comes into play. So when we're talking, so you can't, for example, pull yourself up. You can't push yourself. And one of the consequences of this, which is kind of interesting, is when you're in outer space and you take away air friction, if once an object is moving, you have a little engine in your rocket or satellite, and it gives, and you turn it on for a second or two, and it gives an unbalanced or outside force pushing off against the gas that is ejected. It propels the object forward, and now you can turn it off and save your gas for later. And now this object is going to move with that speed on and on and on. Now, yes, there is some friction in outer space. In every cubic centimeter of space, if this is 1 cubic centimeter, there's one particle, maybe an electron or a nucleus or some other cosmic particle. So there is a little bit of space, but the very, very best vacuums that we can create in the laboratory with our vacuum pumps are nowhere close to being able to duplicate the kind of vacuum outer space is with its 1 particle per cubic centimeter. Here's an example showing you the difference between mass and inertia. The tendency of an object to continue in its original state, we call it inertia. Newton's first law is the law of inertia. Objects in motion keep on moving, objects at rest stay at rest unless an outside force acts on it. And a measure of this amount of inertia is called mass. Mass is this resistance to a change in its motion, whether it's a change in direction or a change in velocity. We say it has its inertial or rest mass. And mass is a scalar quantity. We don't talk about the direction of a 2 kilogram object, for example. And the airbags and seatbelts play a role in this inertia. All right, Newton's second law. We might observe that if I push a object with a certain amount of oomph or force, I can make it accelerate. If I push it with twice as much force, it'll accelerate twice as much. And in other words, acceleration seems to be directly proportional to the force that is acting on it. And if we want to find my proportionality constant, it turns out that proportionality constant, which we could call K is actually the object's mass. And so if we pick the right unit of mass, we won't need a proportionality constant. And that mass then means my expression can be called this. F equals ma. Force equals mass times acceleration. Or if we come over to here, we can also observe that if I push an object with a certain amount of mass, I can get it to accelerate. And if that object has twice as much mass, my acceleration is going to be half as much. It's inversely proportional. But once again, we see that this acceleration is proportional to the force that I push it with, which is why force is in the numerator, and it's inversely proportional to the mass, which is why the mass is in the denominator. And notice that this summation sign, it means the net force, the summation of all of the forces acting on the object. Obviously, if the summation of all the forces equals 0, if the up forces are balanced out by the down forces and the right forces are balanced out by the left forces, and the in forces, represented by an X, the back of an arrow going in, are balanced out by the up out of the page forces, represented by a point, like an arrow coming up towards your face. If all these forces are equal and opposite, then my net force is going to equal, the summation of all my forces is going to equal 0, so there's no net force, which means there is 0 acceleration. But if I do have an unbalanced force, it's going to cause acceleration. In other words, the only way you can have an acceleration is to have a net unbalanced force. When the summation of all my forces does not equal 0, when the summation of all my forces does not equal 0, I have a net unbalanced force, or I could have several net unbalanced forces, which I could add the forces together as vectors in 3 dimensions, and then that net unbalanced force is what's going to cause the acceleration. We can also break it down and talk about my net unbalanced force in the x direction, the y direction, and the z direction, which means we would need to componentize the vectors representing those forces. Now, usually, we're only going to be working with 2 dimensions in first-year physics. In advanced physics, you can work in 3 dimensions, the x, the y, and the z in 3-dimensional Cartesian space. Our unit of force is going to be the Newton, lowercase n here. And and if you think about mass, if my unit of mass is the kilogram, and my unit of acceleration is the meters per second, 1 Newton is a kilogram meter per second. Second squared. That is my unit of force. But of course, that's kind of awkward to keep talking about kilogram meter per second squared because we talk about it so much. So we just call that the Newton. That's 1 Newton is a kilogram meter per second squared. Not to be confused with the old-fashioned, archaic, out-of-date, backwards unit that only your old-fashioned, archaic, out-of-date countries, like the United States, we use the pound. But a Newton is roughly about 1/4 of a pound, which would be 0.25, so just a little bit less than 1/4 of a pound. And I'm going to stop there, and we'll do some practice problems in the next screencast.